Okay, so I'm going to start with some more discussion regarding errors, and that is different combination of errors. So, for example, if we want to determine any unknown quantity x, which is related to two other quantities, suppose y and z. So, if there is some error present in y and some error present in z, how they will affect, or knowing the errors in y and z, how we can predict what should be the error in x. Those combinations will be discussed. So there could be different combinations how x is related to y and z. Suppose there could be a addition relation, then difference between the two, or multiplication in this way. So to discuss the error combinations, first of all, let us consider that the quantity y, we are going to represent it in terms of its true value and its absolute error. So here the small y represents its true value, and plus minus delta y represents the absolute error in y. Similarly for z, this small z would represent its true value, and delta z would represent the absolute error present in z. So these are very simple configurations actually. So let us start with addition. So x is equals to y plus z. Then in order to calculate the error in x, we can easily replace this capital Y and Z with the expression that we just considered over here. After that, if we just group them together, we'll find out that this will represent our true value of x, and this will represent the absolute error present in x. So the absolute error in x is actually the summation of the absolute errors present in both y and z. So if these two values are known, then the possible error in x can be easily predicted. Now for subtraction, we'll get something similar. So in this case, again we can follow the same approach, which will result in this sort of an final form. So here again, small y minus z, we can refer it to be the absolute value of x, and the summation of the absolute errors in y and z is again representing our absolute error present in x. So for both addition and subtraction, the absolute error will be the summation of the errors present in the individual quantities. But for multiplication and division, a direct relationship between absolute error is not possible. However, the relationship can be represented in terms of relative error. So if we have x, which is the multiplication of the two quantities y and z, we can again simply put those two expressions here. And by simplifying, we can write it in this form. So after we write it in this form, if we consider this term, this is supposed to be a very small compared to the other terms, because here only the two errors are multiplied. So the error is supposed to be very minimum if we are considering random error. Then if we multiply these two quantities, it will eventually give us a small value compared to the others. So we can neglect this term and finally refer to y into z as our absolute value of x, and the error present in x will, the absolute value of error present in X will now be represented by this expression, where it cannot be directly referred to I mean the summation of absolute errors between the two quantities like before, but we can represent it in terms of the relative error. So the relative error in X is the ratio between the absolute error divided by the true value of X. So plus minus delta X, we can represent it in terms of this expression. And if we divide it by X, which is YZ, then we will find delta Z by Z plus delta Y by Y. So we can say that in case of multiplication, the relative error in X will be the summation of the relative errors of the quantities of upon which X is dependent on. Similarly, for division, we are going to get a similar expression like we got for multiplication. However, the approach should be a little bit different while determining the while deducing the expression. So for considering the division case, we are going to start with the true value only at the beginning. So after that, we are going to take e-based logarithm on both sides or ln on both sides. So that will give us this expression, and after that we are going to differentiate with respect to X on both sides. So on the left hand side we will get 1 by X, and on the right hand side we can take a partial derivative and expand the terms in this manner. So if we rewrite the expressions on both sides, then we can rewrite them in this form. Now dx, dy or dz, this actually refers to the change in the corresponding quantities. So in this case, the change in X, you can refer it to be the possible error in X. So the dx, dy, dz, you can replace them in terms of their error. So you can further rewrite them as the relative error, and if we take this plus minus outside, we can simply write the combination of the errors to be the summation of the relative errors. Now for both of these cases, the final conclusion is the same. So even if we have an expression like this, w into y by z, even in this sort of an expression, you can say that the overall relative error in X would be summation of the relative errors present in w, y, and z together. Now, moving on, let me discuss about one more combination, that is power of a factor. If X is related to Y and Y is raised to a particular power, suppose n in this case. So similarly, we can follow the approach that we followed in case of division. So we can rewrite it in terms of their true value X equals y to the power n. Take ln on both sides, and after taking this we can take a derivative on or differentiate with respect to x on both sides. So again, on our left hand side we will end up with 1 by x, and on our right hand side we will have n into 1 by y dy by dx. So let us rewrite it in this format and represent the quantities with respect to their errors. So in this case we can say that the relative error in x then would be n multiplied by the relative error in y. So similarly, if you have multiple power of factors relationship like y to the power n multiplied by z to the power m, then for this sort of an expression you can suggest the possible error to be possible relative error to be first of all n into relative error in y. As they are multiplied together, you can put a summation, then m multiplied by the relative error in z. So very simple configurations, some different types of combination that you may have depending on the relationship or equation that you are dealing with, and from the equation you can suggest the possible value of the error present in a particular quantity. Now some basic discussions on statistical analysis related to errors. So normally the statistical analysis are done in order to eliminate or distinguish the effect of random errors, or if you are using different instruments to measure the same quantity, which instrument is providing you the better result. These things you can easily suggest by calculating some or doing some statistical analysis. So first of all, let us start with mean. And you all are familiar with this, that often for any quantity we take multiple readings, then take the mean of it. So that is the purpose of trying to eliminate the effect of the random error, because each time we measure the quantity, suppose if we measure it n times, take n number of readings, each time it might give small amount of deviations. So calculating the mean will actually overall reduce the overall effect of the deviations that we have in each of the uh, individual measurements. So it is nothing by summation I equals 1 to n divided by n. Now it will minimize the random error. However, for distinguishing different data sets, it is not sufficient. So to further analyze, calculating the deviation of each data, deviation from the mean of each data is often helpful. So the deviation d1, suppose for the data x1, it deviates from the mean by this amount, or we can represent it by x bar minus x1. And for d2, we can represent it by x bar minus x2 in this way up to dn. Now, how this can be helpful, I can suggest in terms of considering two data sets. Suppose one is A, one is B. Now, you can consider the data set A is generated by a particular instrument, suppose instrument A, and data set B is generated by another instrument, and both the instruments are used to measure the same quantity. So in dataset A, the values you obtained, suppose they are 102, 104, 106, 108, 110. And in dataset B, all the values are equal to 106. So here, if you consider only the mean value, you will see that the mean for dataset A is 106, and also obviously the mean of dataset B is also 106. So if you only consider the mean, then you cannot differentiate between the performance of the the two different instruments A and B, because your B is actually giving you both precise and accurate data. However, your dataset A is deviating a lot from its mean value, or if the mean is actually giving you the mean value is actually equal to the true value, then you can say that that value is not reproduced repetitively. So the result that you will obtain using this instrument, it might not be trustworthy. So in this way, considering the deviation can often help you in distinguishing the characteristics of two different instruments or two different data sets. And for even further analysis, standard deviation, calculation of a standard deviation will help you further. So you all know how a standard deviation is calculated, right? So can you suggest it? What is the standard deviation? Root of root mean square of the deviations. Okay, so you have to take square of all the deviations that you have calculated, and if you take their average and then take the square root, so the RMS value of the deviations will give you the standard deviation. Now the standard deviation suggests how your data is deviating from the mean. Now if you calculate the overall standard deviation, then you don't have to, once you have calculated it, you don't have to repetitively calculate the deviation each time, because after you know that for a particular instrument this is the possible standard deviation, then when you again measure a particular data, you can already suggest that okay, using this instrument this could be the possible standard deviation. Now this is often helpful in order to analyze datasets which has larger samples, because when you are dealing with a large dataset with larger samples and you are dealing with random errors, so often the distribution of the data sample becomes not, or it has the characteristics of normal distribution. So in case of normal distribution, you guys are familiar with the normal or Gaussian distribution, and you know that that can be represented using a standard bell curve like this, and it is symmetrical with respect to the mean. So the center point is the mean, or I can denote it by mu, and on both sides this is sigma plus sigma, this is minus sigma. So uh, this is for one standard deviation. Now from this plot you can also have a measure of how spread your data is from the mean. Now if I draw another diagram here, suppose this is sigma 1, and if I draw another diagram, and denote the standard deviation of this one as sigma 2. So from these two graphs you can easily see that sigma 1 is greater than sigma 2. So for a particular data set, if you are getting larger standard deviation, you can say your data will be more spread away from the mean value. And if the standard deviation is smaller, then they will be clustered towards the center or towards the mean. So this could be some of the observations that you can do from standard deviation. Now, apart from this, if you can, I mean, if you know that your data samples are normally distributed, then you can also suggest the probable error in the data set, which would be 0.6745. Okay, let me just check whether this constant is correct or not. Yes, it is right. So 0.6745 into sigma. So using this simple formula, you can multiply your standard deviation with this constant term. And if your data set is normally distributed, you can suggest the probable error present in the data set. Now, the discussion so far, I think it is quite straightforward, but if there is any question, you can ask. Otherwise, I will move to the next topic. Yes.
Sorry, I wanted to ask, how did you get this value for the probable error?
This constant term you can determine by deriving through the expression of Gaussian distribution. So if you have studied this before about Gaussian distribution, any normal or Gaussian distribution can be represented by an exponential equation. So if you take the integration on both sides and gradually proceed step by step, then finally you will get a value something like this. So however, that process, the book that I'm following, which is the book of David Bell, they haven't elaborated the process, they have just given the equation. And I also thought that maybe it is not that much necessary, because just I'm giving you some introductory idea. So I haven't shown it over here, but I think the detailed derivation is given in the book of Shawnee. Maybe the chapter is chapter 3. So if you are interested, you can refer to that book. In that book, in step-by-step process, this derivation is available. Any other questions?
So you can move to the next topic.
Okay, in our next topic, we are going to discuss about the measurement of resistances. So different ranges of resistances, high, medium, or low range resistances. So the low, medium, and high range resistances, they are normally classified depending upon their values. So if the value of the resistance is less than 1 ohms, then the resistance is considered to be a low range resistance. If it is between 1 ohms to 0.1 mega ohms, then it is in the medium range, and if it is more than 0.1 mega ohm, then it is a considered as a high resistance. So high resistance is basically the insulation resistances. So the insulating materials used in the cable or in the bus bars or in between transmission lines. So those insulating materials, their resistance is normally considered to be considered as high resistances, and low and medium range resistances are for for the different types of conductors actually. So it might be the windings used in the armature or the field winding of a DC motor, or even the medium range resistances could be the resistance of the transmission lines. So in this way, they are actually classified in 3 categories. Now, for measuring the low and medium range resistances, we are in this course we are going to discuss about some DC bridge circuits. And for high resistance measurement, I'm going to discuss some techniques of direct deflection method, mega ohm bridge method, and I'm going to discuss about a device called Megger to calculate the high resistance or insulating resistance. So for today's class, we are going to start with Wheatstone bridge. Now,
Sir, this classification of resistance is based on DC resistance or AC resistance.
it's based on DC resistance.
So we have different classification for AC resistance.
Is there separate resistances, DC or AC resistance?
Sir, as far as I know, in the AC transmission line, the AC resistance is not as same as the DC resistance. They are separated.
Well, but what we are going to discuss here, we are mostly going to focus on the DC resistances, and also the insulating resistances that we are going to talk about, suppose the high range resistances. So for this course, I'm going to focus on the calculation with respect to DC sources. Okay, maybe what you are saying, maybe that can be further explained by your teacher who has actually taken your power system course. Maybe he can provide you a better idea about what you are suggesting. Okay, so the basic operation of Wheatstone bridge is actually known to you all, so not much to discuss about it uh, here in detail, but uh, uh, the fundamental operation that I can suggest is that it operates in terms of the detection of null deflection by the galvanometer. So when we are obtaining null deflection in the galvanometer, we can suggest the bridge to be balanced. So when the bridge is balanced, the current through the galvanometer is 0, so we can suggest that the potential difference between these two nodes B and D should also be 0. If the potential difference is 0, then if we consider this loop, then the voltage drop across this resistance, if the current is I1 and this current is I2, then the voltage drop across this resistance and the voltage drop across this resistance will be equal, which we can represent as I1P equals I2R. Now, as the current flowing through the galvanometer is passing is 0, so the same current I1 will pass through this resistance Q1, and the same current I2 will pass through this resistance S. So the expressions of I and I2, we can replace it by the voltage source E divided by the overall resistance in the path, that is P plus Q into P, and for this case we can replace it by E divided by R plus S into R, and this will lead us to this relationship among the resistances, from where we can finally get this relation between the four resistances. So if three of the resistances is known to us, we can determine the unknown resistance. So this concept is known to most of you, or all of you actually. You should know this. Now in this today's lecture, I'm going to try to elaborate a bit on the sensitivity analysis of Wheatstone bridge. So three types of sensitivity will be discussed here in this lecture: voltage sensitivity, the bridge sensitivity, and the current sensitivity. So before I start the discussion, I would like to ask you that sensitivity, if it is higher, that is better for us, or if it is lower, then it will be better for us.
So lower,
Why lower?
because then stability will be higher.
But if it is lower, then you will not be able to
The higher voltage.
check smaller changes. If you want to detect smaller changes, then with a low device which is having low sensitivity, you will not be able to check. So it should be as high as possible, so that small change or small unbalance can be detected. So as I was talking about unbalanced conditions, so suppose previously our bridge was balanced with the values of P, Q, R, and S. So if suppose one of the resistances uh, experiences some change in its value for some sort of a variation, suppose increase or decrease in temperature, or it is stressed somehow, so that a change in resistance we can represent here by delta R, and due to that change in resistance, there will be an unbalance in the bridge, and due to that unbalance, the potential difference between the two nodes across the galvanometer B and D will not be zero anymore, so it will have some value. So in order to determine the voltage sensitivity, we need to find an expression for E. In terms of that, we are going to calculate or have an expression of voltage sensitivity in terms of the resulting change in resistance.
Sir, can you please explain the sensitivity, what we are calling the sensitivity?
Okay, so sensitivity is, I can say that the ability of any device to detect a change. Okay, suppose you are using a galvanometer, you are providing or passing through some current through the galvanometer. So uh, until and unless that current is sufficient to uh, give you a deflection in the along the scale, you will not be able to detect any change. So if we say that the galvanometer has a higher sensitivity, we can say that okay, even a small amount of current will be sufficient to give deflection in the galvanometer scale. Or even in case of voltmeter or ammeter, if you consider this term sensitivity, so it is actually related to what small fraction you can detect using that particular meter. So there are some meters that can detect small changes in current, so they are more sensitive, and there are some meters they can detect current or current or voltage at a higher range, so they can be considered to be less sensitive. So did you get a idea about what we are trying to refer through sensitivity?
Yes, sir, I get it now.
So here the main thing is that if we have a change in resistance delta R, how we will formulate some relationships to examine that due to the change in delta R, what will be the effect in the galvanometer deflection. And we will move on to the bridge sensitivity later, but as we are talking about voltage sensitivity, so due to that change in resistance, the voltage across the galvanometer will change. So as the voltage of the galvanometer will change, the deflection in the galvanometer will also change with respect to that. So the voltage sensitivity is referred to be the change in deflection with respect to the change in per unit uh, or per unit change in the voltage difference across the galvanometer. So here theta represents your deflection in the galvanometer, and E represents the potential difference across galvanometer. Now our goal would be to determine an expression of E, and we are going to relate it with delta R. So if we can find an expression of E with respect to delta R, then we can suggest that what would be the voltage sensitivity of the device with the change in resistance delta R. So in order to determine this expression E, we are going to consider the two terminals across the galvanometer to be open circuit, and we are going to do some elementary circuit analysis to find the expression. So this same diagram can be redrawn as it is shown in this slide. So we are going to now focus on this loop. So this voltage drop across P, we can refer it to be EAB, and this voltage drop across R plus delta R, we can refer it to be EAD. If that is the case, then considering this loop or this mesh, we can write E to be equals to EAD minus EAB. Now let us consider that the current flowing through P is I1 and the current flowing through R plus delta R is I2. So similarly, like we did earlier, we can replace this one by I1P and the other one by I2 into R plus delta R. Sorry, I just reversed the quantities. So as this is EAD, so this one should be I2 into R plus delta R, and EAB should be I1 into P. Now I2 we can represent it in terms of the supply voltage as before, like this, and similarly we are going to represent I1 as well. Now for this term we can replace this P divided by P plus Q by R divided by R plus S that we determined in case of the balanced condition. Once we do so, we'll be left with we'll be left with this expression, and after further simplifying, so I am skipping one line here. So after further simplifying, we will have s into delta r in our numerator and r plus s whole square plus delta r into r plus s on our denominator. So to further simplify this expression, we are going to neglect this term here, because we can consider delta r into r plus s to be significantly less than r plus s whole square, because delta r is a small change, and if we multiply it with r plus s, uh, it will not significantly increase the quantity, but rather if it is a fractional value, it will decrease this value, which will definitely be less than r plus s whole square. So we can ignore this term and simplify it to be s into delta r divided by r plus s whole square. Now, putting this expression in the expression which was written in the previous slide for voltage sensitivity, we can write it to be theta into r plus s whole square divided by e into s into delta r. So for a particular arrangement, r, s, e, and this s also, so they are supposed to be constant. So you can in this way relate the voltage sensitivity with respect to the change in resistance. Now from this expression, we can also rewrite theta. So if we rewrite theta, it will be SV into E, and we can say it to be SV into E S delta R divided by R plus S whole square. So I have written it in this form because we are going to later use it again when we are discussing bridge sensitivity and current sensitivity. So I hope that up to this it is okay. Now later on I will move on to discussing bridge sensitivity, and in the meanwhile, if you want to ask anything, you can ask. So as we are talking about bridge sensitivity, so bridge sensitivity is defined as the deflection per unit change in the fractional or per unit fractional change in resistance. So as we are talking about overall bridge sensitivity, so this delta R is actually causing the unbalance in the bridge. So we can refer the bridge sensitivity to be the ratio of the deflection by the fractional change in the resistance. Now, if you want to establish a relation between bridge sensitivity and voltage sensitivity, we can do that by using the expression of theta that I last wrote in the previous slide. So that is SV into E into SR divided by R plus S whole square. So actually, okay, let me elaborate it. So if it is delta R, then we'll have R by delta R. So we are just cancelling these two terms out. So now, in order to further simplify this, we can divide the denominator by the term S into R. So if we divide it by SR, we will have SV into E divided by R by S plus 2 plus S by R. So after we obtain this, we can also represent this in terms of P by Q and represent this in terms of Q by P, as these ratios are equal under balanced condition. Now, as we were discussing that if we can obtain maximum sensitivity, then it will be beneficial for us to detect smaller changes. So can you from this expression, can you suggest what could be the possible condition for maximum sensitivity? Anyone?
Maximizing SV.
Well, for example, you can suppose that SV and E are constant for a particular meter, right? For a particular galvanometer, the SV voltage sensitivity will be fixed, and also the supply voltage is fixed. As we are talking about the bridge sensitivity, you can tune some parameters in the bridge circuit or the ratio arms of the bridge. So that can be done by tuning the values of the resistance that you have on the denominator. So
Maybe have
if you want to
minimize.
maximize it, then you have to minimize the denominator, right?
We can set P and Q both equal to 1.
Yes, we can set them both equal to 1, or we can set them equal, both of them to be equal, because that will give us the minimum value of the denominator. If we increase it or decrease it from 1, then in either way the denominator will start increasing. So for example, if P by Q is equals to 0.5, then this Q by P over here will counterbalance it, and it will give you 2. And overall in the denominator, in this case, you will have 4.5 at the denominator, which is higher than 4 that will get in this case. So for the vice versa case also, your denominator will tend to increase, and the minimum value of the denominator can be obtained when this condition is satisfied. So this could be one condition, and another one could be setting all the 4 resistances to be equal. Now once these conditions are satisfied, then you can further simplify the equation of bridge sensitivity to be SV into E divided by 4. And while you are doing any math, if you see that the question gives you values such that these conditions, any one of these conditions are satisfied, then you can directly use this formula to calculate the bridge sensitivity. Otherwise, if this condition is not satisfied, then in order to calculate bridge sensitivity, you should use the generalized one. Now, lastly, in our today's discussion, let me discuss about current sensitivity. So, in order to determine current sensitivity, we have to consider the current flowing through the galvanometer. So, the current sensitivity is basically defined as the deflection or change in deflection with respect to the amount of current flowing through the galvanometer, or per unit current flowing through the galvanometer. So, in order to further elaborate this term, we should find an expression for the galvanometer current Ig. So this galvanometer current, this is galvanometer current, and in order to find this an expression for Ig, we can consider the Thevenin equivalent circuit of the Wheatstone bridge that we have considered earlier. So any circuit, if we take its Thevenin equivalent, we can represent it in terms of the Thevenin voltage and the Thevenin resistance along with our load. So in this case, as we are focused on determining the Thevenin voltage and Thevenin resistance across these two terminals of the galvanometer, so we can say that our load in this case will be the galvanometer, and for this case we are also going to consider the internal resistance present in the galvanometer. So this, you can refer this to be your node B and this to be your node D, and the current flowing through the galvanometer, I can denote it to be Ig. Now once I do so, then you can say that the current through the galvanometer will be Ig equals E Thevenin divided by R Thevenin plus Rg. Now for determining the Thevenin resistance RTH, we can redraw the diagram which was shown earlier. So as our focus is to determine the Thevenin equivalent resistance across node B and D, so to do that we have to first eliminate the voltage source, and for eliminating the independent voltage source we normally make it a short circuit. So in this case node A and node C will now be the same node, and according to that we can redraw the diagram with respect to node B and D. So if it is our node D, this is node B, then in between them this would be our R plus delta R, this would be S, and this would be P, and this would be Q. And this point is actually indicating the common node here, the node A and C, which are short circuited now. Now our Thevenin, which is actually equal to RBD in this case, so we can easily do it by taking the series parallel combination of the resistances. And for further simplicity, we are going to rewrite it in this form, because of the fact that delta R is very much less than the value of R. Now, as we were discussing about the maximum bridge sensitivity, so if we consider this condition to be satisfied in order to deal with maximum bridge sensitivity, we can further rewrite the expression of R Thevenin to be R square divided by twice R plus R square divided by twice R, so which will eventually give us R. Now, for determining E Thevenin, we don't have to do that whole process again, because we have already did that while we were discussing about voltage sensitivity. Because while finding that expression of small e, we considered the two terminals of the galvanometer to be open circuit, and thus that will be same as the Thevenin equivalent expression of the Thevenin equivalent voltage. And let me rewrite it over here again. So again, for consideration of the maximum bridge sensitivity, this expression can be further written as E into delta R divided by 4R. So once we have done up to this, so next we can uh, put this expression of ETH and RTH in our expression of IG, which was previously written as this. So if we replace ETH, that will give us E into delta R divided by 4 R into RTH plus RG. So we can actually replace this RTH with R in this case, because in the previous slide we have considered that for the condition of maximum bridge sensitivity. So after we have obtained this, now we can rewrite SI to be theta divided by IG, which is equals to theta into 4R into RTH plus RG divided by E into delta R. And to establish a relation between the three sensitivities, so let us consider first the current sensitivity and the voltage sensitivity. So in this case, so if you recall the expression of theta, which was SV into E S into delta R divided by R plus S whole square, we can rewrite it for the maximum sensitivity to be this one. And if we now put the expression of theta over here, we will end up with SV into delta R divided by 4R into 4R RTH plus RG divided by E delta R. So that will eventually give us SV into RTH plus RG. So in this way, we are having a relationship between SI and SP. And to relate all three sensitivities together, we can define the bridge sensitivity as this, as we have derived earlier. And further, we can replace SV with SI divided by RTH plus RG. So this will relate the three sensitivities. Now, while like I said earlier, that these expressions that has been derived, that has been considered, that has been derived considering the condition of maximum sensitivity, bridge sensitivity. Again, if you are encountering some mathematical problems where this condition is not satisfied, then instead of simplifying the value of RTH like what has been done over here, you should use this generalized one to calculate RTH. Later on, you should proceed on calculation of the other quantities. So whether you will use the simplified form or the generalized form, so for that, try to check the question first. So that is from my part today, and if you have any question you can ask. Otherwise we can conclude today's session here. Any questions, anyone? Is there any question?
Assalamu alaikum.
Walaikum assalam.
Yeah, please can you upload the recorded video?
Sorry?
The recorded video. Can you upload it?
Yeah, I will upload the video. I have already uploaded the video in the Google Drive. I have provided you the Google Drive link uh, in Google Classroom, so you can access it from there.
Okay, thank you, sir.
So lecture 1 is already uploaded, and today's one I will upload
Okay, thank you.
a little bit later.
Okay, sir.
Okay, you didn't ask anything, so let me just discuss one more thing. So one of the students from the other session asked that, okay, for this derivation of all the equations, we considered uh, the variation of only one resistance, but what will happen if there is variation in multiple resistances? Suppose along with R plus delta R, there is also variation in S plus delta S, suppose. Then what should be our approach? Then obviously you have to approach the whole thing in a different way. So in that case, when in all the expressions you can, where it is necessary, where the term was there you should use this one, the updated one now. So even for the determination of the Thevenin resistance here, you can write it to be S plus delta S like this, or depending on which resistance is varying. If there are two resistances varying together, then you should take consideration of the variation of both of them in the necessary portions. So if you proceed gradually, step by step, you can easily understand where the changes should be made. So let me conclude over here today. You guys are not responding or saying anything, so I assume that there is no question.